Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
My name is Tom Ball. I'm Group Manager of the Software Reliability Research Group, and it's my pleasure to, I don't know if this is the inaugural lecture, but to kick off the use of this new room, at least for the Software Reliability Research Group in the new Building 99. I'm pleased to welcome Professor Sergio Campos from the University Federal of Minas Gerais in Brazil. He's come a long way to talk with us about formal verification and model checking, and will be a visitor here for the remainder of the week. So if you're interested in chatting with him, please let me know and add him to your schedule. Sergio has worked with many people over the years, including Ed Clark at CMU, and has an interest, wide interests in verification as well as bioinformatics and other areas of the intersection of computer science and other fields. So I'll turn it over to Sergio.
Well, thank you. Thank you very much for having me here. It's a pleasure to be here. And I would like to talk to you today about an explicit symbolic model checker. I am Sergio Campos from Universidade Federal de Minas Gerais in Brazil. And I thought I'd start by talking a little bit of where I come from. So I asked for help, and instead of talking a little bit, I managed to get a video that our department made. It's a promotional video, but it's very short, so you won't be bored for too long. I'll try to play it now. Audio is going to be a little bit improvised as well. We'll see if it works. If it doesn't, we'll give up. Can you hear it?
University of Minas Gerais has been marching in the direction of the future. Excellence in the formation of future professionals is a priority. DCC invests in the field through its undergraduate, continuing education, and graduate courses with master and doctorate programs. 80 bachelor degrees are conferred each year. DCC counts with 50 graduate students and hundreds of students enrolled in their specialization and continuing education courses. The Department of Computer Science has been rated by the Ministry of Education as one of the best in Brazil. 38 professors with master or doctorate degrees coordinate the work being done among the most important in Brazil today in the software and hardware systems development area. An important tool to aid in the accomplishment of this mission is the DCC Library, the largest in its field in the state of Minas Gerais. Its collection consists of more than 14,000 books and periodicals on the subjects of computing, mathematics, and statistics. The library is available to students and researchers of the university and other registered institutions. The Department of Computer Science is responsible for the proper functioning of fundamental aspects of our everyday life. Its excellence has been recognized with numerous awards over the years, both in Brazil and abroad. On the telephone, for example, relies on an important implementation of a telecommunications supervising system developed by the department. Brazilian public educational institution that enjoys the best results in the scientific and technical partnership with industry and the market, having established solid, long-lasting cooperation programs. Through the application of the most sophisticated technology and computer science, DCC is in search of new solutions for our times. 24 hours a day through the use of high-velocity communication links, and in some cases wireless, facilitating access to information, DCC is a fundamental ally in the democratization of the use of computers in Brazil, overcoming obstacles and pulling download barriers. Making up for inadequacies and attaining new limits, opening the doors to a new era, recovering and preserving the memory of the Brazilian people, and defining a new way of looking at the world, which is the fruit of a mutual exchange between DCC and more than 15 university-level institutions scattered over 3 continents. DCC takes on the challenge, right here in the present, of planning our future.
Okay, so that gives you a bit of an idea of where I come from. And now on the topic, I'd like to talk to you about the Explicit-Symbolic model checker. This work has been done by me and a student of mine who has graduated since then. And the presentation was done by him. And after I sent the abstract to Tom, I realized that I didn't have the source code of the presentation, so I couldn't change it, which is a bit risky. Especially because this is the real cover of the presentation. It does not have my name, so I put one so that you know where I am. And Umberto was a student that did the work. And I'm going to be talking a little bit about model checking and the combined explicit-symbolic model checker, which came from an interesting perspective. And when I did my PhD work in the 90s, God, that sounds like thousands of years ago, but it's true. I started thinking, I was learning model checking and started thinking, this is really cool, but at the time everybody talked about model checking hardware. And I'm like, well, hardware is nice, but I like software. I would like to model check software. And people were telling me, oh, you can't do that. I was, well, you know, I have to do that. And then people kept telling me that, well, maybe you can do that, but a symbolic model checker is no good for that. Why not? Well, software is infinite state. And so you have to abstract out the infinite components into a finite model, and this finite model is better represented by an explicit model checker. And I didn't agree with that, and I don't agree that even software is necessarily infinite state. I mean, from what we observe, it's finite. It runs on a computer, which is a finite state machine, right? So I kept doing all of my PhD, and a few years after that, fighting this idea of explicit versus symbolic representations. And every time you come up with an argument that favors one, it can be used to favor the other as well. It doesn't really matter, right? So in some cases, yes, explicit's better. In some cases, symbolic's better. But it's not very easy to characterize that. So I thought, wouldn't it be nice if we could just try it differently? I mean, you get a model, try it explicitly, and try it symbolically. See what happens. Better yet, let's mix them up, right? And that's where this work came from. So I'm going to talk to you a bit about how we've done that. And this is the part that the student knows better than me. We did this explicit symbolic modeling for the intermediate format from Verimag. I don't know a lot about it, but I think I'll manage to show you what the ideas are. Implementation, and talk about some experiments and contributions. So model checking, as you know, is a way of verifying formally a system, hardware or software or anything, right? The system is represented by the means of a finite model. It is exhaustively analyzed to check for properties. It has been successfully used to verify several systems, right, throughout the years. It's been around for decades, really. And the advantages are that it's fully automated and guaranteed to finish, which doesn't help us much in the case that it takes too long, but usually it does not. But it is fully automated, and it generates counterexamples. So model checking is a very useful tool. And a way of describing what we're trying to do is that you have a physical system that you want to verify, for example, an airplane, and you create an abstract model out of it. And you have a property that you want to verify. It won't crash. And you create a formal specification out of it. And you have to give this to the tool so that it will check to see if this property is true or not. So here an example we use this example throughout the lecture. It's a microwave oven example. Does anyone have a pointer? I can't reach that high. Well, anyway, we'll survive. Let's see if I can use this one. So we have an initial state, right? And from here, things can happen. You can close the door, and it gets to stay closed. You can open the door, it gets back. It's a simple model, right? But it shows one type of system we want to verify, right? And so we model things in this formalism. And what we're looking for are paths in this graph. So we're looking for some path that, for example, in this case, we're looking for a path that leads to a state where start, close, and heat are all true, right? And this is one example path. Well, there are several ways of representing this internally. And one way is to use the explicit state representations. In this case, a finite state machine is given by means of a linked list of states, right? So you have the traditional implementation of graphs, and algorithms are used to explore this state by state. You get a state, find out its successors or predecessors or whatever you want, right? And you search all of the possible states in the system. This technique has been successful in dealing with systems usually with few parallel processes, right? Where the number of states is usually small. That doesn't mean that the systems are not interesting. Several very, very interesting and very complex systems have actually a small number of states, right? But this is a characteristic usually associated with explicit state representations. So common knowledge is that it seems to be the best choice for systems with intensive data transformations and software designs, because you tend to abstract out the data transformation or the data values, and then what you have in the end is the control flow, which is usually small, right? Spin and Java Pathfinder are representative tools of this kind of representation. Symbolic model checkers, on the other hand, they use different encodings. In this presentation, we talk encoding of Boolean formulas using BDDs. There are other ways, such as sets over based model checkers, in which you represent your model symbolically, not explicitly. And the trick here is that the representation allows you to change, to look for successors or predecessors of a set of states without enumerating the states. So you have an operation that takes a certain time, but the time it takes, or the amount of space it takes, is not directly related to the number of states it's traversing. And that's the big advantage, right? Usually they are able to handle a very large number of states. It is known as well, it's not suitable for certain arithmetic operations in some types of software. Again, I agree. I say that it can be used for software. It certainly has, and it can be very efficient. I agree, however, that for some types of software, it gets complicated. So, for example, it's well known that BDD-based model checkers or BDD-based anything does not handle multiplication very well. So if you have a certain piece of software in which multiplication is very important for it to work, it's very unlikely that it will work on a BDD-based model checker, right? New SMV and Veros are representative model checkers. Veros is the work that I've done in my thesis. You can download it from CMU. And we see here already that it gets kind of mixed up. So you have a system that has features that are handled well by explicit model checkers and handled well by symbolic model checkers. The problem is that the parts that are not handled well are really inefficient in the representation that you choose. So regardless of what you choose, one or the other, you may run into trouble. So before I show you our approach to how we've done this, just to show you, given a simple graph like that, the explicit representation gives you the transitions from 1 to 2, 2 to 3, etc. And the symbolic representation gives you formulas that says 1 and 2 prime or 2 and 3 prime. So this is the kind of representation. It's very different, right? And the task is, how do we actually integrate them? Well, we try to combine explicit and symbolic representations at the same time. So we want a model with one representation that's hybrid, right? We avoid calling this model checker hybrid because hybrid means usually, continuous and discrete time. So we call them explicit symbolic. But the idea is that you have one representation for everything. Moreover, we want flexibility during the choice of state representations. We want to be able to change the representation of each part of the circuit or the system from explicit to symbolic, right? And allow efficiency requirements to dictate the representation. So I want to get a piece of a system and say, okay, I want these variables to be represented explicitly and these other variables to be represented symbolically, right? Related work is SLAM, where you have an explicit representation for the control flow and a symbolic representation for the data, right? It's one way. It's the traditional way of thinking. It works. But it's, in our example, it's more flexible. You can actually decide which parts are go where. So I'm going to show you, going back to my favorite microwave oven example. This is an interesting example because it seems so simple, and yet we presented it in Brazil in a research center that belongs to an electronic equipment manufacturing company. And while we're talking this, it's saying that, well, this is a microwave oven example. It's, we've come up with this just to show. And then some guy raises his hand and says, well, I am actually a microwave oven controller designer. And, well, I have a few questions about that. So even though it's very simple, it actually makes some sense, we hope. Anyway, what we've done is we've split the variables into explicit and symbolic variables. We've chosen them arbitrarily in this case, and the red ones are explicit, and the blue ones are symbolic. So how do we represent the system in a way that we preserve the functionality? Well, we do projections to create an explicit model and a symbolic model. So in this case, we group the states that have we're doing the explicit modeling. So we group states. So for example, this is not start and close. So these two states, they have the same value for the explicit variable, so they become one state, right? So this is a simple thing to do. And we've done that. We came up with this red model. We can do the same thing for the symbolic one and come up with this other model, right? Now, we don't actually construct these models because we lose some of the connection between the explicit and symbolic. So if we construct these two models separately, we are not going to be able to find out exactly which transition in the combined model corresponds. Well, we can find which transition in the combined model corresponds to one in the explicit and one in the symbolic. What we can do is the other way around. Given an explicit transition and a symbolic transition, I cannot map directly which is the transition in the combined model. So we can't construct them, even though these pictures are, help us understand what's going on. We don't construct them that way. what we do is base our implementation, base our technique on the explicit state model checker. And in this case, we have an example of a transition. You have a transition from state QE to Q prime E1, and from QE to Q prime E2, right? So these are transitions in the explicit state model. And we associate those with a subset of symbolic transitions. So when you go from QE to Q prime E1, you go from QS to Q prime S1 in the symbolic model. So now we are associating with each transition in the explicit model a set of transitions in the symbolic model that correspond to the changes in the system when you go from the explicit state 1 to explicit state 2. And so, here are a few of these transitions in the microwave oven example. You start from not start, not close, and you go to start and not close. This is a transition in the explicit model. But when you do this, you go from not hit, not error to not hit error in the symbolic model, right? So the implementation it's not very complicated, because what we do is we have an explicit state model checker, but to each transition we associate another data structure, a BDD. And this BDD is a set of transitions that correspond, that can happen when you transition in the explicit state model from these states, right? And you can see here that this is a real state, not start, not close, to not hit, not error. I mean, not start, not close, not hit, not error is a state in the actual system. And there is a transition from this state to a state start, not close, not hit, error. So this corresponds to a real transition. To verify this, we conceptually convert everything into the explicit and symbolic states. But we don't follow this procedure because we do this in a mixed way for efficiency reasons. So for example, let's assume that we want to find the states in which not start is true, right? So that's easy because not start is an explicit variable. So we just find out which states are actually satisfying not start. We have not start close, not start not close. But those are not states in the composed model. Those are states in the explicit model. So we have to find out which transitions actually start in those explicit states. And we find that there are a few states that satisfy not start. So you have not start close, hit not error. Because this is the beginning of a transition that goes from ES3 to ES3 and from SS3 to SS2 and SS3. So this is an actual state in the combined model. These two explicit states, they have three transitions leading from them. So we can find, with the associated symbolic transitions, the states, the symbolic states that are associated with these explicit states. And so we find out which are the states that satisfy not start. We can do it the other way around. So if you want to find the states that satisfy error, we look for the transitions in the symbolic model that satisfy error and find out which are the explicit states that are the starting points of those transitions. And in this way, we are able to identify which states satisfy error. Notice that you can do it both ways. If you have you want to look for a state that has a certain property that's half explicit and half symbolic, you can do the same thing. You can just find the explicit states that satisfy that property and then look for the transitions, for the symbolic states in the transitions. We can also traverse this structure in an easy way. So suppose we want to find out the states that satisfy EX close heat. So in this example, we are looking to find out, okay, we have the states that satisfy close. It's this state here ES3 satisfies close, right? So I want to find the predecessors of close heat. So I find that ES1 and ES4, they are predecessors of close. But I have to, the property is actually hybrid, and I have to find out not only predecessors of close, but also of heat. And I find out that from the symbolic transitions that lead to close, only this one satisfies heat in the next state. So you have ES3 satisfies close, SS3 satisfies heat, and they have as predecessors ES4, SS3. So I found out what are the states that satisfy EX close heat in this way. I can do the same thing for all the other CTL operators. And in this case, I want to find out the states that satisfy not start, not error until start error. I get the state start error, which is the blue and red state there, right? And this is the beginning of my search, and I have to search backwards. And I find that ES2, SS1 has as predecessor ES1, SS2, right? So ES2 leads backwards to ES1. It's very simple to see there. And SS1, not heat error, is a state that is the successor of this symbolic transition, and the predecessor is not heat, not error. So I find that not start, not close, not heat, not error is a predecessor of start, not close, not heat, error, right? And it satisfies not start, not error, so I keep searching. And I get to this state as well. And I found out what are the states that satisfy not start, not error until start error. The EG, which is the missing link in the model checker, is done in the explicit fashion. So suppose I want to find out the states that satisfy EG yellow. And I apply a traditional algorithm in which I find the strongly connected components, I mark them, and I find the states that lead to them, right? That also satisfy the yellow condition. So in this way, I manage to implement the explicit symbolic model using an explicit representation associated with symbolic transitions, and I am able to model check it, CTL model check it in a straightforward way. We have applied this to the Verimag Interchange format, which models asynchronous communication in real-time systems. And it's an interesting language. It's aimed at hardware, but it has a rich type of sets and dynamic creation of processes. And it's an interesting language in itself, and it's an interesting language to use as the tool for our model checker as well. So this is an example of an if program. So you define the system, the data, and its range. You define signals and route between these signals and how they connect and what happens in this case. And to model these if descriptions, we create the explicit and symbolic models from them and combine them into our representation. In the explicit model, there is one edge per state per transition, which is traditional. In the symbolic model, you encode them as Boolean functions, in our case, implemented by BDDs, right? So here's an example. It shows a piece of if code that it happens in parallel, and you have if A equals B, it does one thing. If A different than B, it does another thing, right? And what happens is, suppose that we look at the yellow piece of code, and we generate these transitions from it. This is simple translation between this language and the graph. To model, to create the model, we have to compile the code into an explicit representation and into a symbolic representation. In the explicit representation, we do a traditional thing. We've done this. This was an interesting thing to mention, that this started like a really cute idea. It's like, well, let's do this. It's going to be very easy to experiment with. It turns out that it was the opposite, because we had to build both an explicit model checker and a symbolic model checker. And we tried to actually use existing ones. But we couldn't, because they were too large, too complex, and too difficult to integrate. So we ended up building everything from scratch. I think that we've used some of code from Verus, but the explicit state was built from scratch. So it was a lot of work. And what we do is we create transitions from the state vectors between, in the cases that the code allows you to. So we have the source code A equals B plus 2, and you create a transition from 111 to 310. And in this way, we compile it and create the explicit representation. So in this case, we move a little bit backwards, and we find that it's the same transition. If A equals B plus 2, A and B are 1, so you create the transition. On the symbolic model, you create BDDs corresponding to the transitions. So this code, this explanation is taken from Verus, which is a C-like language that is compiled into a BDD model checker, right? And what we do here is, if you want to compile an assignment, x gets the value of the expression, you have as parameters TS, which is the context, which means what you've done so far, and the big TX is the global context, so all of the other transitions. So we ignore the big TX for now. And what we do is, we want to assign the value of the expression to the variable x, right? And we say x equals expression, but we replace the x in the expression by a new variable, and in the context as well. So we say x gets the value of the expression, and in the context that is valid up to this point, but we replace the x's in the context and in the expression with a fresh variable, right? And then we remove the fresh variable, because this fresh variable represents the previous value of the x variable. So we change its name and then remove it, right? In this example, you see how it works. So you say that in the context, you have that a equals a prime, which means that variable a hasn't changed its value since the last transition. And you want to say a equals a plus 1. So the value of the expression of the variable x is a prime, which is the value that a will have in the next state. The evaluation of the expression a plus 1 leads to a prime plus 1. And so you do a prime equals a prime plus 1 substituted for y, and a equals a prime substituted for y, which gives us this expression. A prime equals y plus 1, and a equals y, which is exactly what we want. A prime equals a plus 1. So this works well because there is no conflict between the current and the next value of a. Just another example, the if statement is compiled into, from a given context TS, you generate two contexts, TS prime and TS double prime, where TS prime is the execution of the if statement, provided that the expression is true, and TS double prime is the execution of the else statement, provided the expression is false. and then you conjunct them. So either you do the then or you do the else, right? And if you have an example like that, it's compiled very easily. So previously a equals a prime, there was no change in the value of a, right? And on the second line on the right, you say a equals a prime and a prime equals b prime, because that's the condition to get into the then statement. And then you say a prime equals b prime plus 2 and a equals b prime. And that's the third line then is the result of the execution of the then. And the fifth line is the result of the execution of the else. And then you do a disjunction of all of that, and you get the value of the if statement. I have two models, and the way well, this slide is actually, I think it's unnecessary for the audience. But the question is, you have states and transitions, right? So you have a transition from state A to B and from a certain state C to D. How do you associate the fact that B equals C, for example, which is represented here, and you associate that by the values of the variables? So it's something that I'm sure you know, but for the audience to which this presentation was originally prepared, this was an important point. In the symbolic model, however, it's more interesting, even though it's not too complicated, it's more interesting. How do you actually make sure that you traverse this model and get the values right, and you get the states that you're visiting right? So, for example, in this case, I have a transition to d equals 0, and I do one step, and I get to d equals 1. Now, d equals 1, which is the next state of this transition, is the current state of this next transition. So if you've reached d equals 1, then this now becomes enabled. This now becomes a transition that can be taken. And you get it to d equals 2, right? And then if you do that, d equals 2 leads to d equals 3. But d equals 3 actually leads to leads you back to this explicit state here, but with a different value for the symbolic variables, right? And you do the fixed point calculation. Now, d can be 1 or 3. And then d can be 2 or 0, 1 and 3, and then you reach to a fixed point. So we actually have to keep the states that we visited in both the explicit and symbolic representations to be sure that we find the fixed point in the traditional way. The implementation of, we've done this and we've implemented this. And the implementation both started from scratch, as I told you. We wanted to use Spin and Verus as basis for our work. We had to take ideas from Spin, and we took some code from Verus. It's interesting to point out that in Brazil, the students have a limited amount of time to do their PhDs. It's 4 years. After that, you get an extension for 1 year. And after that, you have to finish. So I convinced the student that we really wanted to get existing model checkers to use this. And I wanted him to actually start on Spin and implement on top of Spin. If you've noticed, the technique is based on the explicit model checker. So in my mind, it would be easier to start with Spin and add the symbolic parts to it, right? But because of the time restrictions that he had to graduate, we couldn't do this. We had to do it from scratch. It was faster to do that. It turned out to be quite an exciting time for non-technical reasons, because the student was getting close to his 4th year, and he had very little results. And he was not from my city. He was from Natal, a city in the beach in the northeast coast of Brazil. And so he took a vacation and went to visit his parents. And I told him, like, I shouldn't go there because, you should spend this 2 weeks working because, you take the risk of not finishing in time. He says, no, I have to go. So he went there. And while he was there, they were hiring professors at his home university. but they required him to have, this professor, to have a PhD. So he signs off as a candidate for this position, and it's a public university, and as is mine. And public universities, the hiring process is regulated by law, and it's very complicated. So if you miss a step, you're just kicked out of the system, and you can't do anything about that. So he enrolled in the process, and the requirement was that he had to present a demonstration of completion of his PhD studies by this date. This was mid of the year, like June, July, and he knew he had to present the proof that he had finished his PhD by February next year, and he had very, very little results. But he took the exam, and he passed. So he comes back and says, now I have to finish. And I look at him and says, why are you telling me this? Finish, right? And he got into this crazy mode that he started implementing things and writing papers and doing all of that. And I told him, it's like, you have to be lucky, because in order to defend your thesis, you have to have at least one publication that's, you know, of a certain characteristics. And I don't know if we're going to find a conference that meets these requirements with a deadline so close by that you can finish your paper, but that you can also have the result until the time. And we were lucky to find one. And he wrote the paper was accepted. And I told him, now you have to finish your implementation. And he had 3 months to do it. And he decided that he could forego sleeping for 3 months, and he did it. And in the end, it was, you know, I got kind of worried, because he told me that he was so stressed up about this that he didn't sleep while he was implementing it. And then after a while, he couldn't sleep at all. But he managed to do it. But this story is, he managed to do it, he graduated, and he went back to his university, and by March he had his proof, and they postponed calling him from February to March. So everything worked out fine for him. But this is the reason why we had to do it from scratch. And even though it's an interesting story in itself, it has a consequence that we found out this, by this time we found this out, that we wanted, as everybody does, we wanted to get the good running times. We wanted it to run faster than anything on Earth, right? Obviously, that's what we all want. But we found out that this was never going to be the case, because both of our lags, the explicit and the symbolic, were just too rudimentary. We just implemented them to get it running. There were no optimizations whatsoever, so we couldn't get good running times, right? But we set up for a plan that we wanted. What I wanted him to do was to get at least one example in which it would run better in the combined model, better than in either explicit or symbolic. This would show that the technique actually means something. We got this result. It's not presented here, and this is actually the weak point of this work, because it was a very small example, but we managed to do this. So in our implementation, properties are specified in CTL, right? And in the explicit representation, it's a traditional one in which we associate the BDD with the transition. We had to do compression of the state vector, which is traditional, easy to do, and necessary. Otherwise, it won't run. It will be just too slow. Explicit states were cached. There was some specific queue modeling that I must confess I don't remember the details of. There was some rudimentary static analysis for the explicit model as well, in which you shrunk the number of bits for the state counters, and we did some optimization to get it running. The experimental results in this case and this example are very preliminary, and they don't actually convince us of much. That we have the microwave oven, it's, you know, a variation of that, but not much more complex than that. it ran very fast on both explicit and symbolic, and it took more time on the combined model. But this kind of is explained because you have to do so much housekeeping to control these two models that for simple models, it's kind of expected that it will take longer in the combined model. There was another counting example in which the symbolic model was much better. The combined model was still worse, even though the compilation time was better in this case, right? In the end, we managed to get an example in which the combined model was faster than either the explicit or the symbolic model, which showed that the two make sense. But I must confess that we need more experimentation on this just to see how it works. The neat thing about this technique is that we can play with the variables as much as we want. So we can do what SLAM does. Say, get the weight counter, the program counter variables explicit and everything symbolic. This is what SLAM does. Now let's flip it. What happens? Probably it's not going to be as good. But let's see, maybe. Now let's see. This variable here, it's used in a lot of ifs. So it's actually a control flow variable. It's not data. It's a variable that's used to control where you go. Let's move that to the explicit representation and see if it gets better or not, right? Well, this is the kind of thing that we can do with this tool that in other tools it's not so easy to do. Well, so we found that representation of the model has a significant impact on the efficiency. As I said, explicit and symbolic can be used simultaneously, but the explicit need aggressive optimization. So our running times, I mean, these are just toy examples, but our running times wouldn't be very interesting because you really, to get interesting numbers, you really have to use optimizations, particularly in the explicit state model checker, which the naive implementation of is very inefficient. A naive implementation of a symbolic model checker is less inefficient than explicit state. So we could live with the symbolic without a lot of optimizations, but not in the explicit. So the main contributions of this work are flexible environment for integrating different model checking approaches. I've been thinking about, since this, about how would we go about adding set-based model checker to this stuff? It would be an interesting thing to consider. I mean, you could have explicit set, BDD set as well, or maybe the three of them. I don't think the three of them would work. Well, not in this framework, but replacing one of them with set would be a very interesting experiment to try, right? It allows us to compare representations in some sense, in a fairer way, because I've played this game several times that you want to say that your model checker is better than the other representation, right? And then you get your favorite example and you model it. And you model it on the other representation model checker to compare, and you get better running times. But this is for two reasons, usually. It's because it's your favorite example. I mean, of course, you want to get good running times for your tool, right? And so the example is not necessarily aimed at the other kind of representation. It's unavoidable, but it's still okay. The worst part for me is that you're familiar with your model checker. You're not familiar with the other model checker, so your modeling in the other model checker is usually not very efficient, right? I had a very interesting experience. I've played this game a few times, and there were some people that worked with Spin that played this game with Varus. So from time to time, they sent me email asking me, how do you represent this in Varus? They didn't tell me why they were doing this, but I know they were comparing it, right? And I told them how it should be done, and they just, thank you very much. They never gave me the result. And I am absolutely sure that it was an unfavorable comparison to my model checker. But it's okay. I mean, that's what you can do, and that's what you have to do. You have to do at least some measure of comparison. And I think that the fact that they asked me how I would be modeling this or that feature shows that they were serious about it, and I was perfectly happy to answer them. But again, this comparison has some strong limitations. Now, in this case, it's much simpler because it is the same tool. And you can't actually compare the running times either because of the efficiency of the optimization considerations, right? But it's closer to a fair comparison, right? So we have a prototype for this. We use the language of the interchange format, which, looking back, I don't think it was the best idea, but it worked for us at the time. So, future works, optimizing it would be nice. I think that at this point we'd have to throw it away and do it again with a more efficient model checker. A dynamic change of representations is something that would be interesting to try. But I must say that I don't think that, or this conversion between explicit and symbolic during the checking, I don't think that's going to be very useful. If for no other reason, then the conversion time between the representations would add up to probably not be very efficient in the end, but it's something to try. So the idea here is to use both explicit and symbolic techniques in an integrated fashion. I think this is the message here, is that it's at this point, it's silly to be saying that explicit's better, symbolic's better, or set is better. We've got to have all of them. In the real world, you have to have all of them, because there are some examples that work with one and not with the other, right? And this is one way in which we can do this in a way that you can experiment. Suppose that you don't know what this is all about. I mean, you don't know which representation this is going to be better. Suppose that you have a group in which two people argue that, no, this is symbolic because of this feature, and this is explicit because of this other feature, right? So you could use this to test. Even if it's not the most efficient model checker, you could test that and say, well, see, the symbolic representation or the explicit representation tends to be better for this example. So let's model it in spin, or let's model it in USMV or whatever, but you would do it not blindly as we do it today, or guessing, which is what we do today. And so that's the idea. It's a prototype implementation, not very efficient, but it's been fun anyway to do this. So thank you.
Thank you very much. Question? So let me just say that there's another notion of explicit that has been championed here previously at Bell Labs by Patrice, and I think is picking up a lot of steam even for verification. So the idea is, with programs, explicit just run the program. So if you have, I mean, not even a model, but if you have a program and you have some test data, you can learn just by running the program. And then, but the interesting thing is, how can you sort of take that testing approach and sort of merge it with a verification approach, which uses symbolic means. So we have a number of projects around this the same idea, but instead we think of the explicit as just being concrete runs of an actual program, and then the goal is to somehow use the symbolic techniques to help the concrete, to help guide us towards unexplored parts of the state space.
Which is a natural extension of this LAM idea. That sounds very interesting. It's kind of a symbolic simulation, right? Symbolic simulation, you simulate it for the hardware, but with the symbolic value. So it's a similar idea, as I understand.
Right, although the idea is you can actually just first run the program on some inputs, and then just have totally concrete values, no symbolic, and then generalize from those concrete inputs to symbolic.
Mm-hmm. Okay. Sounds interesting. Okay.
Okay, great. Thank you.
Thank you.